So we started this lesson with finding the domain and a range from graphs. Now what we're going to look at is what does it mean to find the domain of a function from an equation? So what we're looking for are what are the possible values for x, or what can x not be? So I want to make a big deal about the fact that really there's only two things that can restrict a domain at this point for us. The first one being when there's an x in a denominator. If you graph y equals 1 over x, you get a graph that looks like this. What it is that your graph will do something funky around x equals 0. So if I were to draw a vertical line here at x equals 0, you'd notice that your graph kind of diverges away from it. We call this asymptotic behavior. So what it is that there's a line that is there, it's called an asymptote, that your graph approaches but can't cross. Because if I put in x is equal to 0, anything divided by 0 is undefined. And so your graph's going to do this weird swoopy thing. Now, we're not going to have to graph rational functions at this point, but I just wanted to show you what it looks like so that you know that there's a restriction in the domain, right? There's something that x cannot be. So I like to say the domain is the set of x such that x is an element of the real number system, meaning x can be anything, but it can't be 0. Now, the back of the book simplifies this. It just says this, right? It's like x, the set of x such that x can't be 0. It's assumed that you know that x can be everything but, right? So this is a simplified form. Now it's funny, they go from not liking set notation for domain and range to not minding set notation for restrictions in the domain. So this is set notation, perfectly acceptable, but they also always give interval notation. So this is the interval notation saying, hey, x can be everything but 0. So your graph goes from negative infinity up to 0, not including it, or anything from 0 up to infinity. Okay, so anytime you have an x in a denominator, your denominator cannot equal 0. The other place you're going to find restrictions is if there's a radical. So if there's an even index, so a square root or a fourth root or a sixth root, you cannot take an even root of a negative number because the square root of -1 doesn't exist. So if you have a radical in your equation, then you have to know that your graph won't exist to the left of 0, right, for this one. So to say that, we'd say the restriction is x has to be greater than or equal to 0. And so from a set notation, which again, all of a sudden the textbook's okay with, you can say it's the set of x such that x is greater than or equal to 0. You don't have to include the xer part. You can leave that off. I just like it because it's saying, hey, x can be everything, but has to be greater than or equal to 0. Or interval notation, you can just say 0 to infinity. Okay, so how do we do this? Well, you're going to look at your equations. So first off, I want to identify which equations are going to have restrictions in the domain. So the conditions are there should be a radical and or a denominator where there's an x in the denominator. So if you look at this guy, there's a restriction. Okay, there's an x in the denominator. If you look at this guy, there's a restriction. There's an x in the denominator. This one, there's no x's in denominators, and there's no radicals either. So even though there's this funky absolute value thing, there's nothing I can't put in for x. So for the domain, this one would be negative infinity to infinity, which is interval notation, or again, if you like set notation, x can be anything because there's nothing I can't cube. There's nothing I can't take the absolute value of. So there's absolutely nothing I can't put in for x as long as it's real. This one has an x and a radical. All right, so these three are going to have domain restrictions. This one is not. So let's start with this guy. So again, when there's an x in the denominator can't equal 0. So x minus 3 cannot equal 0. So if I add 3 to both sides, solving this linear equation, I get x cannot equal 3. So from a set notation perspective, you'd say the domain is the set of x such that x cannot equal 3. If you wanted to do this in interval notation, you'd say x is everything up to 3, whoops, not -3, up to 3, or 3 up to infinity. All right, what about this guy? I kind of debated whether I should put this one in, and I think I must have looked in the textbook and found a question that was like it, because we're going to review how to solve quadratic equations. But really, we're going to start off by saying, hey, x squared plus 2x minus 3 cannot equal 0. Well, what values of x would make this equal to 0? Well, you can't tell when it's in this form. So anytime you have a quadratic, you can solve a quadratic by factoring, square root method, completing the square, and quadratic formula. Now, if none of those words mean anything to you, don't worry, we will review those later. And I'll say that any question that's chosen at this point will be factorable. So it is assumed that you can factor trinomials. And if that is a wrong assumption, make sure you find the just-in-time in the back of the book that practices factoring. But what it is that we are going to put this into a product of binomials. And we're going to say that x times x is what gives us x squared. So I'm allowed to just go straight to these two brackets. I don't have to do decomposition. I'm looking for two numbers that multiply to give me -3 and add to give me +2. So that's going to be +3 and -1. So for this one, I'd say that x plus 3 cannot equal 0. Remember the zero factor property? And x minus 1 cannot equal 0. So x cannot equal -3, x cannot equal 1. So if I was to write this in set notation, I'd say it's the set of x such that x cannot equal -3 or 1, and call it good. Interval notation, everything from -infinity up to -3. Then from -3 to 1. Then from 1 to infinity. I think that's why they all of a sudden allow set notation, is because that's really annoying to write. All right, and then moving on to when there's radicals. So when there's radicals, the rule is you can't take the square root of a negative number. So 3 minus x has to be positive. In other words, it has to be greater than or equal to 0. There's a lot in this question, so I chose this one specifically because it's going to have this negative x. So you could add x to both sides right now and say that x is less than or equal to 3. But I just want to show you or remind you maybe what happens if you divide by negative. So let's say I was solving for x and I wanted to keep the x on the left. I get negative x is greater than or equal to -3. And then to get x by itself, I would divide by -1. When you divide by a negative across an inequality sign or multiply, you have to flip your inequality sign. So this would be x is less than or equal to 3, which is the same answers that we would have gotten if we'd added x to that side. So from a set notation, I would say the element of the set of x such that x is less than or equal to 3. Or I could put that in interval notation, which would be -infinity up to 3 square bracket because it's equal to. All right, so that is looking at equations and finding the domain. So again, we found the domain when you look at a graph. Now we're finding domain by looking at an equation. And the only thing that will restrict a domain is if there's an x in a denominator. Denominators cannot equal 0. And if there's an x under a radical sign, you cannot take the square root of a negative number. So whatever's underneath the radical sign has to be greater than or equal to 0. The last thing kind of takes a step backwards, I feel, but I decided to keep the order of the textbook, and it's applications of functions. So you'll notice a lot of chapters actually follow this flow. It's like learn a bit about something, maybe solve some equations, and then applications. So this is an application of functions, and what it is they're going to give you a function equation. But you have to read the equation to know what this function equation means. So it says, or the question, I don't know if I said equation, but the linear expansion of a bridge. So this is an equation demonstrating the linear expansion of a bridge. So the linear expansion L, so L is representing the linear expansion of the steel center span of a suspension bridge that is 1,420 meters long, is a function of the change in temperature T. In other words, how much a steel bridge will expand or contract is dependent on the temperature. So the linear expansion, or the expansion of the bridge, is dependent or is a function of temperature. And this is the equation that defines that function. So there's more down here. It says where 0.0 is the coefficient of linear expansion, which is, if you're taking physics, that's a great thing to know, right? And L is in meters, blah, 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 blah. So a lot of this information, like the 1420 and this number here, it makes you feel like you want to use them. And I'm saying blah, 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 because that's what they use to come up with this equation, okay? you don't have to know how they came up with the equation. You're allowed to just use it. So what you have to discover from the words is what the L stands for and what the T stands for, and then use it. So it says find the linear expansion of the steel center span. So find the L when the change in temperature, T, is 30 degrees and 56 degrees. So in other words, we're plugging in T is 30, and then we're going to plug in T is 56. And we're going to see what would be the linear expansion for the steel in meters. So when we plug in 30, we've got 0.0000. I find people mess this up all the time. It's like copying numbers of zeros. So 1, 2, 3, 4. I'm just being careful. So 4 zeros, 1, 3. The dot just means multiplied by 1420 multiplied by 30. So if we plug that into our calculator, decimal 0.0001, whoops, forgot a 0, see there we go, 4 zeros, 0.000013 times 1420 times 30 would be 0.5538. Now this didn't tell us what to answer to, so I'm just going to keep it all. It's usually pretty safe to say one decimal place if they don't specify, but if I don't specify, I won't expect you to know. And so whatever you give me, I'll take. So what that is when there's a 30-degree temperature change, your steel will expand by 0.55 meters, or 0.5538 meters. So how much would expand if the temperature change was 56 degrees? Well, 0.123 zeros times 1420 times 56. Is there a big change? Decimal 0.00013 times 1420 times 56 gives you 1.03376 meters. So when there was a 26-degree more temperature difference, we got almost double the expansion. And so that means that you have to allow for that in your building materials, that there's going to be this expansion and contraction of the metal. All right, so that is 1.2 over with. Good luck on your quick checks and then your quizzes.